Let me tell you about something extraordinary, a question that sounds simple, but opens up the deepest mysteries of physics, biology, and the nature of human existence. It's a question that every child who has looked up at the stars has wondered, and that scientists have spent careers trying to answer. How far can humans actually travel in space before they die? The answer is not what you expect. It's not a discouraging limit that confines us to our cosmic neighborhood. It's not a boundary that imprisons humanity on Earth or even in our solar system. Farther than you think. Far, far, farther than you think. The physics of the universe, properly understood, opens doors that seem impossible when you first hear about them. The limits are real. Biology constrains us. Engineering challenges us. The vastness of space humbles us, but they're not where most people imagine. In a single human lifetime, with technology we can envision building, a person could travel to distances that boggle the mind. They could cross the Milky Way galaxy. They could reach other galaxies. They could, in principle, travel to the edge of the observable universe. This sounds like science fiction. It sounds impossible, but it's not. It's physics, the same physics that governs everything in the universe, understood correctly and applied to the question of human space travel. Let me take you through this extraordinary journey, because understanding how far we can actually go requires understanding some of the deepest truths about space, time, and the nature of reality. Let me start with the naive answer, the answer that most people assume must be true. Space is vast. The nearest star system, Alpha Centauri, is about 4.4 light years away. That means light traveling at 300,000 kilometers per second, the fastest speed possible, takes 4.4 years to get there. A conventional rocket, like the ones that took us to the moon, travels at speeds around 40,000 kilometers per hour. At that speed, reaching Alpha Centauri would take over 100,000 years. No human could survive such a journey. Even our fastest spacecraft ever, the Parker Solar Probe, which reached speeds of about 700,000 kilometers per hour, would take over 6,000 years to reach Alpha Centauri. Still far beyond a human lifetime. From this perspective, interstellar travel seems impossible. The distances are simply too vast, and our speeds are simply too slow. We appear to be trapped in our solar system by the tyranny of distance. But this perspective is wrong. It's based on a fundamental misunderstanding of how space and time work. The key insight comes from Einstein's special theory of relativity, published in 1905. Relativity tells us that space and time are not what they seem. They're not the fixed absolute background that Newton imagined. They're flexible, interconnected, and they behave in ways that defy everyday intuition. The most important feature of relativity for space travel is time dilation. Time does not flow at the same rate for everyone. If you're moving relative to someone else, your time flows differently than theirs. The faster you move, the more dramatic the difference. At everyday speeds, the speeds of cars, planes, even rockets, the difference is tiny, unnoticeable. But as you approach the speed of light, the effect becomes enormous. Let me give you some numbers to illustrate this. If you travel at 90% of the speed of light, time on your spacecraft passes at about 44% the rate of time on Earth. For every year that passes on your ship, about 2.3 years pass on Earth. At 99% of the speed of light, time on your ship passes at about 14% the rate for every year on your ship. About 7 years pass on Earth. At 99.9% of the speed of light, time on your ship passes at about 4.5% the rate for every year on your ship. About 22 years pass on Earth. At 99.99% of the speed of light, time on your ship passes at about 1.4% the rate for every year on your ship. About 70 years pass on Earth, and it keeps going. The closer you get to the speed of light, the more dramatic the time dilation. At 99.9999% of the speed of light for every year on your ship, about 707 years pass on Earth. This changes everything about space travel. The question is not how long the journey takes in Earth time, it's how long the journey takes in ship time. And with sufficient speed, ship time can be compressed to fit within a human lifetime, even for journeys that span thousands or millions of light years in Earth time. Let me work through a specific example to make this concrete. Suppose you want to travel to Alpha Centauri, 4.4 light years away. At 99.9% of the speed of light, the journey takes about 4.4 years in Earth time, slightly more, because you can't quite reach light speed. But in ship time, thanks to time dilation, only about 0.2 years pass less than 3 months. You could leave Earth, travel to another star system, and arrive having aged only a few months. The journey that seemed to require millennia can be accomplished in a single season. But Alpha Centauri is just the beginning. Let's think bigger. The center of our Milky Way galaxy is about 26,000 light years away. At 99.9999% of the speed of light, you could reach it in about 37 years of ship time. A journey that spans half the galaxy, accomplished in less than a typical career. The Andromeda Galaxy, the nearest large galaxy to our own, is about 2.5 million light years away. At 99.99999% of the speed of light, you could reach it in about 35 years of ship time. Another galaxy in a single human lifetime. Let me push this even further. The edge of the observable universe is about 46 billion light years away. Can we reach it within a human lifetime? The calculation is remarkable. If you could accelerate continuously at 1g, the acceleration due to gravity at Earth's surface, a comfortable acceleration that would feel like normal gravity on your ship, you could travel extraordinary distances. Starting from rest and accelerating at 1g, you would reach the speed of light, or rather, approach it asymptotically in about 1 year of ship time. But you don't stop accelerating. You keep going. In about 10 years of ship time at 1g acceleration, you would cover about 10,000 light years. In about 20 years, you would cover about 2 million light years, enough to reach Andromeda. In about 30 years, you would cover about 2 billion light years. In about 45 years, you would cover enough distance to reach the edge of the observable universe. This is astonishing. A person born on Earth could, in principle, travel to the edge of the observable universe and still have years of their life remaining when they arrived. The entire cosmos, everything we can see with our most powerful telescopes, is accessible within a single human lifetime. Farther than you think. Indeed. Now let me be clear about what this means and what it doesn't mean. The traveler experiences a journey of 45 years, but Earth experiences something very different. Due to time dilation, while 45 years pass on the ship, billions of years pass on Earth. By the time the traveler reaches the edge of the observable universe, Earth's sun has long since burned out. Humanity, as we know it, is gone. The traveler has reached their destination, but they can never return to the world they left. This is the trade-off that relativity imposes. You can travel immense distances in your own lifetime, but you do so by essentially traveling into the future. The world you leave behind ages and changes while you're gone. A journey to another galaxy is also a journey to an unimaginably distant future. For some purposes, this trade-off might be acceptable. If humanity wanted to spread to other galaxies, to establish a presence across the cosmos, we could do so. Travelers could reach distant destinations within their lifetimes, establish colonies, and begin new chapters of human history, even knowing they could never return to the Earth they left. For other purposes, the trade-off is devastating. If you wanted to visit another star and return to tell your friends about it, you couldn't. By the time you got back, everyone you knew would be long dead, not just dead, but potentially extinct for millions or billions of years. Relativity gives with one hand and takes with the other. It opens the universe to human exploration, but closes the door to round-trip journeys that fit within normal human relationships and timescales. Now let me address the practical challenges. The physics allows these journeys, but can we actually achieve the speeds required? The energy requirements are staggering. Accelerating a spacecraft to near light speed requires enormous energy. The faster you go, the more energy you need. As you approach the speed of light, the energy requirement approaches infinity. You can never quite reach light speed, no matter how much energy you apply. Let's calculate what this means in practical terms. The kinetic energy of a spacecraft moving at 99.9% of the speed of light is about 22 times its rest mass energy. The rest mass energy is given by Einstein's famous equation E equals mc squared. For a modest spacecraft of 1,000 tons, comparable to the International Space Station, the rest mass energy is about 9 times 10, 19 joules, roughly the world's total energy consumption for 2 years. At 99.9% of light speed, the kinetic energy would be about 22 times this, or 2 times 10, 21 joules. This is roughly the world's total energy consumption for 50 years. And that's just the kinetic energy. If you want to decelerate at your destination, and you do, if you want to stop there, you need to double this. And if you want to accelerate the fuel itself, the requirements become even more extreme. With chemical rockets, the kind that took us to the moon, these journeys are completely impossible. Chemical rockets produce too little energy per kilogram of fuel. You would need vastly more fuel than spacecraft, which would need more fuel to accelerate the fuel, and so on. The exponential math doesn't work. Even nuclear rockets, fission or fusion, struggle at these speeds. They're far better than chemical rockets, but the energy requirements still exceed what we can practically provide. The most promising propulsion concepts for near light speed travel are antimatter drives and laser propulsion. Antimatter is the ultimate energy source. When matter and antimatter meet, they annihilate completely, converting 100% of their mass to energy. Compare this to nuclear fusion, which converts about 0.7% of mass to energy, or nuclear fission, which converts about 0.1%. An antimatter rocket could, in principle, accelerate a spacecraft to near light speed with a reasonable ratio of fuel to payload. The physics works. The problem is producing the antimatter. We can make antimatter in particle accelerators, but only in tiny amounts, a few nanograms per year worldwide. Making the kilograms or tons required for interstellar travel would require vast increases in production capacity and efficiency. The energy required to make the antimatter would be enormous. You'd have to generate and store more energy than the final journey requires due to inefficiencies in production. This isn't impossible, just extremely difficult. An advanced civilization with access to enormous energy sources, perhaps from solar power collectors around the sun or from fusion reactors, might be able to produce the antimatter required. But it's beyond anything we can do today. Laser propulsion is another promising concept. Instead of carrying fuel, the spacecraft is pushed by a powerful laser beam from home. The spacecraft carries a large sail that reflects the laser light, gaining momentum from the photons. The Breakthrough Starshot project, funded by Yuri Milner and supported by Stephen Hawking before his death, proposes exactly this approach. The goal is to send tiny spacecraft, just a few grams, to Alpha Centauri at 20% of the speed of light, arriving in about 20 years. Scaling this up to human-carrying spacecraft is much more challenging. The laser power required scales with the mass of the spacecraft. For a human-carrying vessel of, say, 100 tons, The laser power would need to be trillions of watts, far beyond current technology. But again, this isn't impossible, just extremely difficult. An advanced civilization could, in principle, build the required lasers. The physics allows it. The engineering is the challenge. Now let me consider the biological limits. Even if we had the propulsion technology, human bodies are fragile, space is hostile. What are the actual biological limits on how far humans can travel? The most immediate limit is acceleration. Humans can tolerate high accelerations for short periods. Fighter pilots experience up to 9G in extreme maneuvers. But for long-duration travel, we need sustained acceleration, and the human body has limits. At 1G, the acceleration due to Earth's gravity, humans are perfectly comfortable. We evolved under 1G, and our bodies are adapted to it. Spacecraft accelerating at 1G would feel like standing on Earth's surface. Passengers could walk around normally, eat normally, live normally. At 2G, activities become more difficult. You feel twice your normal weight. Walking is tiring. Lifting things is hard. But humans can function at 2G for extended periods. At 3G or more, prolonged exposure becomes dangerous. The cardiovascular system struggles to pump blood against the increased gravity. Organs are stressed. Long-term health effects become serious. For practical interstellar travel, we should probably assume accelerations of 1G to 2G comfortable enough for humans to live normally during journeys that might last years or decades. The good news is that 1G acceleration is sufficient for remarkable journeys. As I calculated earlier, accelerating at 1G continuously, you can cover enormous distances in surprisingly short ship time. The edge of the observable universe in 45 years, Andromeda in 20 years, the center of the galaxy in 12 years. The second biological limit is radiation. Space is filled with radiation cosmic rays, solar radiation, the radiation environment of any propulsion system. I've discussed space radiation extensively in other contexts, so I'll summarize here. Cosmic rays are the biggest concern for long-duration space travel. They're high-energy particles from outside our solar system, and they're very difficult to shield against. On Earth, we're protected by the atmosphere and magnetic field. In deep space, there's no such protection. The radiation dose on an interstellar journey would depend on speed and shielding. At near-light speeds, the radiation environment changes. Cosmic rays coming from ahead are blue-shifted to even higher energies, while those from behind are red-shifted to lower energies. The net effect depends on the details. Shielding helps, but adds mass. Active shielding, using magnetic fields to deflect charged particles, might be more effective for high-speed travel. The engineering is challenging, but not impossible. The radiation limits on interstellar travel are serious, but probably not prohibitive. With appropriate shielding and medical countermeasures, humans could likely survive journeys of decades to centuries in deep space, though with elevated cancer risk and other health effects. The third biological limit is the lifespan itself. Even without the hazards of space travel, humans don't live forever. The oldest humans have lived to about 120 years. Most people die much younger. This sets a fundamental limit on how far a single human can travel. If we assume a maximum lifespan of about 100 years, and we want to leave time for the traveler to actually do something at their destination, we need to reach our destination within, say, 50 to 80 years of ship time. At 1G continuous acceleration, 50 years of ship time would get you about 50 billion light years from Earth beyond the edge of the observable universe. At 80 years, even farther. So human lifespan is not the limiting factor for traveling anywhere in the observable universe. The physics of time dilation compresses even the most distant journeys into a human lifetime. In part 2, I want to explore more deeply what these journeys would actually be like, the experience of traveling at near light speed, the strange relativistic effects that travelers would encounter, and the profound implications for human civilization if we ever achieved this capability. So we've established the extraordinary truth. Thanks to time dilation, a human being could travel to the edge of the observable universe within a single lifetime. The physics allows it. The limits are not where most people imagine them to be. Now I want to explore what these journeys would actually be like. What would a traveler experience at near light speed? What strange phenomena would they encounter? And what are the deeper implications of relativistic travel for our understanding of space, time, and human existence? Because understanding how far we can actually travel requires understanding what that travel would be like, the wonders and the challenges that await anyone who ventures to the edge of what physics allows. Let me start by describing the experience of acceleration. Imagine you're aboard an interstellar spacecraft, beginning your journey to a distant star or galaxy. The ship is equipped with some advanced propulsion system, perhaps antimatter engines, or a powerful laser sail capable of sustained acceleration at 1 g. As the engines ignite, you feel yourself pressed into your seat, but the sensation is familiar. It feels exactly like normal gravity. You could stand up, walk around, pour a glass of water. Everything would behave as it does on Earth. The floor of the ship is actually the rear wall, perpendicular to the direction of acceleration, and everything falls toward it, just as things fall toward Earth's surface. During the acceleration phase, life aboard the ship would be remarkably normal in terms of physical sensation. You would have artificial gravity not through rotating sections or exotic technology, but simply from the acceleration itself. This is a tremendous benefit as it avoids all the health problems associated with long-term weightlessness, bone loss, muscle atrophy, fluid redistribution, cardiovascular deconditioning. The ship accelerates continuously after 1 day. At 1 g, you're traveling at about 850 kilometers per second, already faster than any spacecraft ever built. After 1 week, you're at about 6,000 kilometers per second. After 1 month, you're at about 25,000 kilometers per second, nearly 10% of the speed of light. As weeks turn to months, you continue to accelerate. You don't feel any different. The 1 g acceleration feels exactly the same whether you're moving at 1% or 99% of light speed. But the universe outside your windows is beginning to look very strange. Let me describe the visual effects of relativistic travel because they're among the most striking aspects of the experience. As you approach the speed of light, several effects combine to transform your view of the cosmos. First is aberration. Light coming from different directions appears to shift toward the front of your ship. Stars that would normally be beside you or even behind you appear to crowd toward the direction you're traveling. It's as if the entire sky is being compressed into a smaller and smaller region ahead of you. At 90% of light speed, stars that should be at 90 degrees from your direction of travel directly to your side appear at only about 26 degrees from forward. The sky behind you becomes almost empty, while the sky ahead becomes crowded with stars. At 99% of light speed, the effect is even more extreme. Almost the entire sky appears compressed into a small cone ahead of you. Looking back, you see only darkness, not because there's nothing there, but because all the light has been aberrated forward. Second is the Doppler effect. Light from objects ahead of you is blue shifted. Its wavelength is compressed, shifting it toward the blue end of the spectrum. Light from objects behind you is red shifted. Its wavelength is stretched, shifting it toward the red. At high speeds, these shifts become extreme. Light that was originally infrared and visible to human eyes gets blue shifted into the visible range. Light that was originally visible gets blue shifted into the ultraviolet or even X-ray range. Looking ahead, the stars would appear intensely blue, then violet, then invisible as their light shifts beyond what your eyes can detect. Looking behind, stars would redden, then fade to infrared invisibility. The combined effect is otherworldly. Ahead of you, instead of the familiar star field, you would see a brilliant ring of light, the entire forward sky compressed into an intense blue-white circle. Behind you, darkness. The universe would seem to close in around you, tunneling toward your destination. Third is the searchlight effect. Objects ahead of you appear brighter, while objects behind you appear dimmer. This is partly because of the aberration, concentrating light from a larger area of sky into a smaller apparent region, and partly because the blue-shifted photons carry more energy. The intensity of the forward view can become problematic. At very high speeds, the energy concentrated in that forward cone could be damaging not just to eyes, but to the spacecraft itself. Shielding would be necessary not just for cosmic rays, but for the intense radiation from aberrated starlight. Now let me describe what happens when you reach cruising speed. For a journey to a nearby star, you might accelerate for months, coast at high speed, then decelerate for months. During the coasting phase, with engines off, you would experience weightlessness, the familiar condition of astronauts on the ISS. For longer journeys, the most efficient approach is continuous acceleration. You accelerate at 1g for the first half of the journey, then flip your ship around and decelerate at 1g for the second half. This way, you maintain artificial gravity throughout, and you arrive at rest relative to your destination, rather than flashing past at 99.99% of light speed. The turnaround at the midpoint is a dramatic moment. Halfway to your destination, the engines shut off briefly, and you experience a moment of weightlessness. The ship rotates 180 degrees so that the engines now point forward, then they reignite, and you feel the 1g acceleration again, but now it's slowing you down rather than speeding you up. During the deceleration phase, the relativistic effects reverse. The compressed forward sky begins to expand again. The intense blue light reddens. The ring of light spreads out into a normal star field. As you slow down, the universe returns to its familiar appearance, and you approach your destination at a reasonable speed for arrival. Now let me discuss the time dilation experience from the traveler's perspective. Time dilation is the most profound and counterintuitive aspect of relativistic travel. The traveler experiences time normally. Seconds feel like seconds, hours feel like hours, years feel like years. There's no sensation of time being stretched or compressed. Clocks on the ship tick at their normal rate. But the traveler is out of sync with the rest of the universe. Suppose you're traveling to Alpha Centauri at 99% of light speed. The journey takes about 4.4 years in Earth time. But aboard your ship, only about 0.6 years pass about 7 months. From your perspective, you left Earth, spent 7 months aboard the ship, and arrived at Alpha Centauri. But when you contact Earth, you discover that 4.4 years have passed there. Friends and family have aged more than 4 years, while you aged only 7 months. This asymmetry is real. It's not an illusion or a measurement artifact. If you had a twin who stayed on Earth, that twin would actually be older than you when you arrived, even though you're genetically identical and started at the same age. The effect becomes more dramatic at higher speeds and longer journeys. If you travel to the center of the galaxy, 26,000 light years away, at 99.9999% of light speed, the journey takes about 26,000 years in Earth time, but only about 37 years in ship time. You age 37 years, Earth ages 26,000 years. When you arrive at the galactic center, human civilization on Earth, if it still exists, would be unrecognizably different. The pyramids of Egypt would be as ancient to that future humanity as the last ice age is to us. Every person you knew, every institution you were familiar with, every aspect of the culture you came from, all would be gone, transformed, forgotten. And yet, to you, only 37 years have passed. You remember Earth clearly. You might still feel like the same person who left. The journey has transported you not just across space, but into the deep future. This is the existential reality of relativistic travel. It's not just a trip to another place, it's a one-way journey into another time. The traveler becomes a temporal exile, forever separated from their origin point in time, even if they return to the same location in space. Now let me explore the implications for communication during these journeys. As you travel at near light speed, communication with home becomes increasingly difficult. Light takes time to travel. If you're 1 light year from Earth, a radio message from Earth takes 1 year to reach you, and your reply takes another year to get back. The round trip communication time is 2 years. But at near light speed, the situation is more complex. You're moving away from Earth almost as fast as your messages travel. A message sent from Earth when you're 1 light year away won't catch up to you for much longer than 1 year because you're racing ahead of it. The details depend on your exact speed, but the practical effect is that communication becomes progressively more difficult as your journey continues. Messages from home arrive ever less frequently from your perspective, and your messages take ever longer to reach home. For a journey to another galaxy, communication becomes essentially impossible. Even at light speed, a message from Earth to the Andromeda galaxy takes 2.5 million years. By the time any reply could return, 5 million years would have passed on Earth. Whatever you had to say would be absurdly out of date by the time it arrived. This isolation is one of the most profound challenges of relativistic travel. You're not just far from home, you're cut off from home in a fundamental way. No phone calls, no video chats, no staying in touch. Once you leave forever. Some proposed solutions involve sending information rather than maintaining real-time communication. You could send compressed updates about your journey, knowing they would be received years or millennia later. You could receive updates from Earth, knowing they were sent years or millennia in the past. But it wouldn't be a conversation, just one-way transmissions across the void. Now let me discuss what happens at the destination. Suppose you've completed your journey, 37 years of ship time to the center of the galaxy, or 20 years to the Andromeda galaxy, or 45 years to the edge of the observable universe. You've arrived. What now? The first challenge is that you're alone. You've traveled farther than any human has ever gone. There's no infrastructure at your destination, no space stations, no supply depots, no other humans. Everything you need must have been brought with you or must be obtainable at your destination. If you've traveled to another star system, there might be planets to explore potentially habitable worlds, resources to exploit, places to establish a colony. Your journey could be the first step in human expansion to another star system. If you've traveled to another galaxy, the situation is similar but more extreme. You've crossed an immense void and arrived at a place teeming with hundreds of billions of stars, each potentially with its own planets. The opportunities are vast, but so is the isolation. If you've traveled to the edge of the observable universe, you're in truly uncharted territory. You've reached the limit of what we can currently observe from Earth, not because space ends there, but because light from farther away hasn't had time to reach Earth since the Big Bang. Beyond the observable universe, there might be more universe, potentially infinitely more, but we can't see it from Earth. From your position at the edge of the observable universe, you would have a different observable universe. You could see things that Earth-based astronomers can never see, regions of space that were beyond our horizon but are within yours. You would be exploring not just space, but the limits of cosmic observability. The second challenge is that you can never go home. Not really. You could, in principle, turn your ship around and travel back to Earth. The physics allows it, but time dilation works in both directions. The return journey would take the same ship time as the outward journey, but an equal amount of Earth time would pass. If you travel to the center of the galaxy in 37 years of ship time, The return would take another 37 years of ship time. You would arrive back at Earth 74 years older than when you left, but Earth would be 52,000 years older, 52 millennia, more than twice the span since the last ice age. Whatever humanity had become in your absence, it would have evolved almost beyond recognition in your further absence. You would be returning to a world as alien to your memories as your memories would be to its inhabitants. For journeys to other galaxies, the numbers become absurd. A round trip to Andromeda would take about 40 years of ship time, but 5 million years of Earth time. The sun would still be shining, but Earth's biosphere would have experienced millions of years of evolution. Homo sapiens might no longer exist, either extinct or evolved into something else. For journeys to the edge of the observable universe, return is cosmologically impossible. The round trip would take about 90 years of ship time, but about 90 billion years of Earth time. By then, the sun would be long dead, the Milky Way would have merged with Andromeda and other galaxies, and the universe itself would be in a different cosmic era, dark, cold, dominated by the remnants of dead stars and evaporating black holes. So while you can travel extraordinarily far in a human lifetime, the price is separation. Relativistic travel is fundamentally a one-way process, not because you can't return spatially, but because you can't return temporally. Now let me explore the deeper implications of these limits. The physics of relativistic travel creates a peculiar kind of cosmic horizon, not a barrier in space, but a barrier in social connection. Within the solar system, communication is slow but manageable. Light takes about 8 minutes to travel from Earth to the Sun, about 4 hours to reach Neptune. Conversations are awkward but possible. You can send a message and receive a reply within a day. Within a few light years, the distance to the nearest star's communication becomes more difficult but still conceivable. Messages take years, but they arrive. You could, in principle, maintain a correspondence with someone on Alpha Centauri, even if each exchange takes nearly a decade. Beyond a few light years, communication becomes increasingly strained. At 100 light years, a round-trip message takes 200 years, several human generations. The correspondence would span lifetimes. The person who sent the original message would be long dead before any reply arrived. At cosmic distances, millions or billions of light years, communication as we understand it becomes meaningless. Messages would take millions or billions of years. The entire history of human civilization is shorter than the round-trip communication time to the Andromeda galaxy. This creates what we might call the communication horizon, the distance beyond which meaningful communication with home becomes impossible. For practical purposes, this horizon is measured in light years or at most light decades. Beyond it, travelers are on their own. But there's another horizon, the return horizon. This is the distance beyond which returning home would mean arriving in a future so distant that nothing familiar remains. For most people, the return horizon is quite close. If you value returning to a recognizable Earth with people you know still alive, you're limited to journeys of a few years of ship time, which corresponds to a few light years of distance at very high speeds. If you're willing to return to an Earth where your generation is gone, but human civilization continues, you can travel farther, perhaps tens of light years, or even hundreds. If you're willing to return to whatever Earth has become, regardless of how alien, you can travel farther still, thousands of light years, or even to other galaxies. And if you're willing to never return to leave Earth forever, knowing you'll never see it or anything like it again, then the entire observable universe is open to you. This is the trade-off that the physics imposes. Distance and connection are inversely related. The farther you go, the more you leave behind. Now let me discuss the implications for human civilization. If relativistic travel became possible, it would transform human civilization in profound ways. First, it would enable the expansion of humanity to other star systems and eventually other galaxies. This expansion would not be quick by Earth-based standards. Colonies at nearby stars would take years or decades to establish, and contact with them would be slow. But it would be possible. Over centuries and millennia, humanity could spread through the galaxy. Each new colony would be largely independent, too distant for effective governance from Earth, too isolated for rapid communication. Human civilization would fragment into a multitude of separate cultures, each evolving independently. Over millions of years, these separate branches of humanity might diverge significantly, culturally, technologically, perhaps even biologically. They might become different species, adapting to different environments on different worlds. The unity of humanity would give way to a diverse family of human-descended civilizations. Second, relativistic travel would create strange social dynamics. Imagine a traveler who leaves Earth at age 30, travels to a star 50 light years away at 99.9% of light speed, spends a few years there, and returns in ship time. The round trip takes about 7 years. The traveler returns at biological age 37. But on Earth, 100 years have passed. Everyone the traveler knew is dead. The great-grandchildren of their friends are now elderly. The traveler is a living anachronism, a person from a century ago preserved by time dilation. If relativistic travel became common, society would have to adapt to these temporal dislocations. People would leave and return at different rates of aging. Family relationships would become complicated. A child might age faster than a traveling parent, becoming older than the parent while the parent is away. Some science fiction has explored these dynamics. The novel The Forever War by Joe Haldeman depicts soldiers fighting an interstellar war, returning from each deployment to find Earth decades or centuries advanced. The cultural and personal disconnection is profound. Third, relativistic travel would raise deep questions about identity and continuity. If a person travels far enough, they become cut off from their past in a fundamental way. The world they knew is gone. The people they loved are dead. The culture they came from has been replaced by something new. In what sense is such a person still the same person who left? They have continuity of memory and body. They remember their past life, even though that past is now unrecoverably distant. But they have no continuity of relationships, community, or cultural context. Some might find this liberating, a chance to start fresh, unburdened by the past. Others might find it devastating, a loss of everything that gave life meaning. The psychological challenges of extreme relativistic travel would be unlike anything humans have faced. In part 3, I want to explore the ultimate limits, what physics really allows, what might extend those limits even further, and what all of this means for humanity's long-term future in the cosmos. So we've established the extraordinary reach of relativistic travel, how time dilation allows a human being to cross the observable universe within a single lifetime, and we've explored what those journeys would be, like the strange phenomena travelers would experience, and the profound implications for human connection and civilization. Now I want to push to the ultimate limits. What does physics really allow? Are there ways to extend human reach even farther? And what does all of this mean for humanity's long-term future in the cosmos? Because understanding how far we can actually travel requires confronting the deepest questions about space, time, and the nature of existence itself. Let me start by examining the hard limits that physics imposes. The most fundamental limit is the speed of light. Nothing can travel faster than light in a vacuum, about 299,792 kilometers per second. This is not a technological limit that might be overcome with better engineering. It's a fundamental feature of the structure of space-time. Why can't anything travel faster than light? The answer lies in Einstein's special relativity. As an object accelerates, its mass effectively increases. It becomes harder and harder to accelerate further. As you approach the speed of light, the effective mass approaches infinity, and the energy required to accelerate further approaches infinity as well. You can get arbitrarily close to the speed of light. If you have enough energy, you can reach 99% of light speed, 99.9%, 99.99%, 99.999%. Each additional 9 requires more energy than all the previous acceleration combined. But it's possible with sufficient energy. But you can never reach 100%. There's always that remaining fraction. Light speed is an asymptotic limit, approachable but never attainable for anything with mass. This seems like a severe constraint. If you can never reach light speed, doesn't that limit how far you can travel? Not as much as you might think. Thanks to time dilation, the ship time for a journey approaches 0 as your speed approaches light speed. At 99.9999% of light speed, the ship time for crossing the galaxy is about 37 years. At 99.99999% of light speed, it's about 12 years. At 99.9999999% of light speed, it's about 4 years. The closer you get to light speed, the more distance you can cover in a given amount of ship time. There's no hard limit on distance, only on speed. Given enough energy to approach light speed closely enough, you can travel any distance within a human lifetime. The practical limit is not physics, but engineering. How close to light speed can we actually accelerate a spacecraft? With antimatter propulsion, we might achieve 99% or 99.9% of light speed. With more advanced technologies, perhaps higher. Each improvement in propulsion technology extends the practical range of human travel. But there's another aspect of physics that might extend our reach even further: the expansion of the universe. The universe is expanding. Every galaxy is moving away from every other galaxy, carried by the stretching of space itself. This expansion is not a motion through space, it's the space between galaxies literally increasing. For nearby galaxies, the expansion is slow to significantly affect travel times, but for very distant galaxies, the expansion is fast. In fact, galaxies beyond a certain distance are receding from us faster than light. This sounds like it contradicts what I said about the speed of light being the ultimate limit, but it doesn't. The speed limit applies to motion through space. The expansion of the universe is not motion through space, it's the growth of space itself. There's no contradiction, just a subtle distinction. What does this mean for travel? If you aim for a very distant galaxy, one that is currently receding faster than light, you might never reach it. The expansion of space could carry your destination away faster than you can approach it, even at near light speed. This defines what we might call the cosmological horizon for travel. It's not just about how far you can travel in a human lifetime, it's about whether your destination will still be reachable as space expands. Current calculations suggest that galaxies currently more than about 16 billion light years away are receding faster than light and will never be reachable, no matter how fast we travel. The expansion of space has already carried them beyond our cosmic reach. But galaxies closer than this, including everything in the observable universe within that horizon, are theoretically reachable. The journey might take a long time in Earth years, but in ship time, it could fit within a human lifetime. So the practical limit for human travel, set by cosmic expansion, is roughly the size of the observable universe. Within that volume, containing hundreds of billions of galaxies, each with hundreds of billions of stars, humanity could potentially travel anywhere, given sufficient technology. Farther than you think, indeed. Now let me explore some speculative possibilities that might extend human reach even beyond what conventional physics allows. These are not established science. They're theoretical possibilities, ideas that emerge from our best theories but have not been experimentally verified. I present them not as certainties, but as illustrations of how rich and strange the universe might be. The first possibility is wormholes. A wormhole is a hypothetical tunnel through space-time connecting two distant regions directly. If you could create a wormhole between Earth and a distant galaxy, you could travel from one to the other almost instantly without crossing the intervening space. Wormholes are allowed by general relativity. They're valid solutions to Einstein's equations. The most famous solution is the Einstein-Rosen bridge, discovered in 1935. It describes a wormhole connecting two black holes, but there are serious problems with using wormholes for travel. First, the wormholes that emerge naturally from general relativity are not traversable. They collapse too quickly for anything to pass through. The Einstein-Rosen bridge, for example, forms and then pinches off so fast that not even light can cross before it closes. To create a traversable wormhole, one that stays open long enough for a spacecraft to pass through, you would need exotic matter with negative energy density. This is matter that has properties unlike any matter we've observed. It would have gravitational repulsion rather than attraction. Does exotic matter exist? We don't know. Quantum field theory suggests that small amounts of negative energy density can exist under special circumstances. The Casimir effect, for example, involves negative energy density between closely spaced conducting plates, but the amounts are tiny, and it's unclear whether they could be scaled up to stabilize a wormhole. Second, even if traversable wormholes were possible, creating them would be an enormous engineering challenge. You would need to manipulate space-time itself, bending it into configurations that don't naturally occur. This would require energy and technology far beyond anything we can currently imagine. Third, wormholes might create causality paradoxes. If wormholes allowed faster-than-light travel in any meaningful sense, they might also allow travel backward in time with all the logical problems that entails. Some physicists believe that the laws of physics would prevent this, perhaps by making wormholes unstable whenever they threaten to create paradoxes. Despite these challenges, wormholes remain a fascinating possibility. If they could be created and stabilized, they would eliminate the tyranny of distance entirely. Any point in the universe could be reached almost instantly. The cosmological horizon would become irrelevant. The second speculative possibility is the Alcubierre drive. In 1994, physicist Miguel Alcubierre proposed a theoretical mechanism for faster-than-light travel that doesn't violate relativity. The idea is to warp space-time around a spacecraft, contracting space ahead of the ship and expanding it behind. Inside the warp bubble, the spacecraft isn't moving through space at all. It's sitting still in a bubble of flat space-time. But the bubble itself is moving, carried along by the warping of space. Since the speed limit applies to motion through space, not to the movement of space itself, the bubble could move faster than light. The Alcubierre drive is mathematically consistent with general relativity. It's a valid solution to Einstein's equations. And unlike wormholes, it doesn't obviously create causality paradoxes, though this point is debated. But there are serious problems with the Alcubierre drive too. First, it requires enormous amounts of exotic matter, matter with negative energy density, to create the warp bubble. Early calculations suggested the energy equivalent of the entire mass of Jupiter would be needed in exotic matter form. Later refinements have reduced this estimate, but the requirements are still vast. Second, there are concerns about the physics inside the warp bubble. The spacecraft would be causally disconnected from the space ahead of it, unable to send signals forward or receive information from its destination. How would you steer? How would you stop? Third, the bubble might accumulate high-energy particles as it travels, releasing a devastating burst of radiation when it stops. This could make the Alcubierre drive a weapon of mass destruction as much as a mode of transportation. Fourth, like wormholes, the Alcubierre drive might create causal paradoxes. The relationship between faster-than-light travel and time travel is subtle but troubling. Any technology that allows faster-than-light travel in one reference frame allows backward time travel in another reference frame. This might mean the laws of physics prohibit such travel outright. Despite these challenges, the Alcubierre drive represents a tantalizing possibility. If the engineering challenges could be overcome, it would allow travel to any point in the universe in arbitrary short time, perhaps even arriving before you left, from certain perspectives. The third speculative possibility is suspended animation or extreme life extension. If we can't make journeys shorter, perhaps we can make lives longer. Suspended animation, reducing biological processes to a near halt, would allow humans to survive journeys of arbitrary length without experiencing that length subjectively. If you could be frozen at the start of a journey and revived at the end, a journey of 1,000,000 years would feel like no time at all. This is not as far-fetched as it might seem. Some animals already do something like this. Tardigrades, the microscopic water bears, can survive desiccation and extreme cold for decades, then revive when conditions improve. Wood frogs freeze solid during winter and thaw out alive in spring. For humans, the challenges are greater. Our large, complex bodies don't freeze well ice crystals damage cells. But research into cryopreservation continues. Small organisms and some tissues have been successfully frozen and revived. The technology might eventually be extended to whole human bodies. If suspended animation worked, the limits of human travel would be set not by human lifespan, but by the durability of the spacecraft. A ship that could function for millions of years, maintaining its structure, its course, its cargo of frozen humans, could travel anywhere in the observable universe, regardless of how long the journey took. Life extension offers another approach. If human lifespan could be extended to thousands or millions of years, journeys that now seem impossibly long would become merely lengthy. A 1,000-year trip to a distant star system would be a significant commitment, but not a life-ending one. This might sound like science fiction, but there's serious research into the biology of aging. Some organisms appear not to age, certain tortoises, some species of fish, possibly some jellyfish. If we could understand and replicate their mechanisms, human lifespan might be extended dramatically. Combined with time dilation, extreme life extension could open enormous distances. A person who lives for 1,000 years and travels at 99.9% of light speed could cover tens of thousands of light years in their lifetime. The galaxy would be within reach. Now, let me consider what all of this means for humanity's long-term future. If the physics allows it, if we can travel to other star systems, other galaxies, perhaps eventually anywhere in the observable universe, what would humanity's future look like? One possibility is expansion. Humanity spreads outward from Earth, colonizing first the solar system, then nearby stars, then the galaxy, then other galaxies. Over millions and billions of years, human-descended civilizations populate the cosmos. This expansion would not be a unified empire. The distances are too great, the communication too slow for any central authority to govern. Instead, it would be a diaspora, a spreading of human seed across the universe, each colony evolving independently, adapting to its local environment, developing its own culture and technology. Over time, these separate branches of humanity might diverge so far that they're no longer recognizably the same species. They might not recognize each other as kin. They might become as diverse as all of Earth's life is today, descended from a common ancestor, but radiating into countless different forms. This is a magnificent vision, humanity transformed from a single species on a single planet into a cosmic phenomenon as diverse and widespread as life itself. Another possibility is consolidation. Instead of spreading outward, humanity might focus on deepening our presence in a limited region, perfecting our civilization, exploring the depths of knowledge and experience, transcending the limitations of biological existence. If we develop technologies for uploading consciousness into artificial substrates, we might not need physical travel at all. We could send information instead of matter, transmitting copies of ourselves across the cosmos at the speed of light. A light-speed signal to the Andromeda Galaxy would take 2.5 million years. But from the perspective of the transmitted consciousness, which experiences no time during transmission, the journey would be instantaneous. You would effectively teleport across the universe, your consciousness reassembled from information at the destination. This approach has its own philosophical challenges. Is the transmitted copy really you, or just a copy? Does the original continue to exist, creating two of you? These questions about identity and continuity don't have easy answers. Another possibility is that we discover we're not alone. The universe might already be filled with intelligent life. Other civilizations might have been traveling between stars for millions or billions of years. We might be latecomers to a cosmos already populated by diverse intelligences. If so, our future would be shaped by contact with these others. We might join a galactic community, learning from civilizations far more advanced than ours. We might face competition for resources and territory. We might be welcomed, ignored, or in the worst case, exterminated by civilizations that see us as a threat. The search for extraterrestrial intelligence continues, and so far we've found nothing definitive. But the universe is vast, and our searches have covered only a tiny fraction of it. The question of whether we're alone remains open. Now let me explore the deeper meaning of these possibilities. The question, how far can humans travel before they die, is not just a technical question. It's a question about the human condition, about our place in the universe, about what kind of future is possible for us. For most of human history, the world was small. A person's horizon was limited to their village, their region, perhaps their nation. Travel was difficult and dangerous. The idea of crossing oceans, let alone reaching other planets, was inconceivable. Over the past few centuries, our horizons have expanded enormously. We've explored every continent, mapped every ocean, visited every corner of Earth. We've extended our reach to the moon and sent robots to every planet in our solar system. The world that once seemed infinite is now familiar, even small. The question of interstellar travel represents the next expansion of horizon. Can we break free of our solar system? Can we reach other stars? Can we spread across the galaxy and beyond? The physics says yes. Time dilation opens the universe to human exploration in ways that aren't immediately obvious. A person born on Earth today could, with sufficient technology, travel to another galaxy and still have years of life remaining when they arrived. This is extraordinary. The universe is not a prison. The distances are not barriers. The stars are not forever beyond our reach. The physics that seems to limit us the finite speed of light actually enables us through the strange gift of time dilation. But the physics also imposes a price. Relativistic travel is fundamentally a one-way journey. You can reach distant destinations, but you can't return to the world you left. The expansion of human reach comes with the loss of human connection. This is the bittersweet truth at the heart of interstellar travel. We can go farther than we think, but in going far, we leave behind everything we know. The universe opens to us, but the door to home closes behind us. Some would see this as a tragedy. The explorers who ventured to distant stars would be exiles, cut off from their origins, alone in an indifferent cosmos. Their journeys would be one-way trips into the unknown, with no prospect of return. Others would see it as a liberation. The explorers would be pioneers, founders of new worlds, progenitors of new civilizations. They would carry humanity's legacy to the stars, ensuring that even if Earth perishes, something of us survives. Perhaps both perspectives are valid. Perhaps interstellar travel is both loss and gain, ending and beginning, death and birth. Perhaps the explorers would be simultaneously the last representatives of the old world and the first citizens of the new. Now let me address the question of motivation. Why would anyone undertake such a journey? The costs are enormous. You would leave behind everyone you know, everything familiar, every connection to your past. You would travel into a future so distant that nothing of your original world would remain. You would face dangers and hardships beyond any that humans have faced before. Why would anyone choose this? One answer is curiosity. Humans have always been explorers. We crossed oceans in fragile boats, trekked across deserts, climbed mountains, descended into caves. We went to the moon not because it was easy, but because it was there. Some people are driven by an irresistible desire to see what's over the horizon, to know what's out there, to push the boundaries of the known. For such people, the chance to travel to another star, another galaxy, another universe, this would be the ultimate adventure. The cost would be worth it for the experience, for the knowledge, for the sheer wonder of seeing things no human has ever seen. Another answer is purpose. Humans are meaning-seeking creatures. We want our lives to matter, to contribute to something larger than ourselves. What greater contribution could there be than carrying humanity's presence to another star, founding a colony that might flourish for millions of years? The explorers would be like the founders of ancient civilizations. Their names might be remembered for millennia. Their decisions might shape the future of worlds. They would be the ancestors of countless generations, the originators of new branches of humanity. Another answer is survival. Earth is fragile. We face existential risks, asteroid impacts, supervolcanic eruptions, nuclear war, climate catastrophe, pandemics, artificial intelligence gone wrong. Any of these could end human civilization or even the human species. The only way to ensure humanity's long-term survival is to spread beyond Earth, beyond the solar system, beyond any single point of failure. A humanity that exists on multiple planets, multiple star systems, multiple galaxies, such a humanity would be robust against any local catastrophe. The explorers would be humanity's insurance policy, our backup, our hedge against extinction. Their journeys would not be abandonment of Earth, but protection of everything Earth has produced. Another answer is simply that some people have nothing to lose. A person who has no family, no deep connections, no attachment to a particular place, such a person might welcome the chance to start fresh somewhere new, even if somewhere new means a different star system. The motivations would be as diverse as the people who felt them. Some would go seeking adventure, others seeking meaning, others seeking escape. Some would be visionaries with grand plans, others ordinary people looking for a new life. And some would be born into it. Once interstellar travel begins, children would be born on starships, grow up knowing no other life. For them, the journey would not be a choice but a heritage, a destiny inherited from parents who made the choice for them. Now let me consider what interstellar civilization might actually look like. If humanity spreads to the stars, the resulting civilization would be unlike anything that has existed before. First, it would be fragmented. The distances between colonies would be so great, the communication so slow, that no unified governance would be possible. Each colony would be effectively independent, making its own decisions, developing its own institutions, evolving its own culture. This fragmentation could be a weakness, lack of coordination, duplication of effort, potential for conflict, but it could also be a strength, diversity of approaches, resistance to catastrophic failure, freedom to experiment. Second, it would be asynchronous. Different parts of the civilization would exist at different points in history, depending on how they were settled and how much time had passed. A colony settled 10,000 years ago might be ancient and decadent, while a colony settled recently might be vigorous and expanding. Travelers moving between colonies would experience this asynchrony directly. A person who left a young, dynamic colony might arrive at an old, settled one, or vice versa. The sensation of moving through time as well as space would be constant. Third, it would be diverse. Different colonies adapting to different environments would develop different technologies, different social structures, different biologies. Some might be recognizably human, others might be so changed as to be almost alien. This diversity could lead to mutual incomprehension, even conflict. But it could also lead to exchange of ideas, cross-fertilization of cultures, a richness and variety that no single civilization could achieve alone. Fourth, it would be sparse. Even a civilization spanning the galaxy would be a thin scattering of islands in an ocean of emptiness. The galaxy contains hundreds of billions of stars, each separated by light years of void. A civilization that colonized 1 million star systems would still occupy only a tiny fraction of the galaxy. This sparseness would shape the civilization's character. Most of space would be wilderness, unexplored, and unoccupied. The sense of cosmic isolation, of being small creatures in an immense universe, would never disappear. Now, let me bring this exploration to a close by reflecting on what we've learned. The question, how far can humans actually travel in space before they die, has a surprising answer. The naive answer, based on conventional rockets and intuitive physics, suggests that we're trapped in our solar system, that interstellar distances are insurmountable, that the stars are forever beyond our reach. But the correct answer, based on relativistic physics and time dilation, is far more expansive. A human being in a single lifetime could travel to another galaxy, could travel to the edge of the observable universe, could travel anywhere that physics allows, which is essentially everywhere we can currently see, farther than you think. The universe is open to us in ways that aren't obvious until you understand the physics. But this openness comes with costs. Relativistic travel is one way in time, if not in space. Travelers become temporal exiles, separated from their origins not by distance, but by elapsed time. The world they leave behind ages and changes beyond recognition, while they age only years or decades. This is the fundamental trade-off that physics imposes. You can go anywhere, but you can't go home. You can travel to the stars, but you can't return to the Earth you left. You can see the universe, but you can't share what you see with those who stayed behind. Whether this trade-off is worth making is not a question physics can answer. It's a question about values, about meaning, about what makes life worth living. Different people will answer it differently. Some will say the universe is too precious to explore at such cost. Better to tend our garden on Earth, to perfect our civilization here, to find meaning in our immediate connections rather than in cosmic wandering. Others will say the universe is too vast to ignore. Better to accept the cost, to make the journey, to carry human consciousness to the farthest reaches of existence. If the price is temporal exile, so be it. The reward is the cosmos. I don't know which answer is correct. Perhaps both are correct for different people. Perhaps the future will include both those who stay and those who go, both those who deepen and those who expand. What I do know is that the universe is open. The physics allows us to go farther than we think. The limits are not what most people imagine. The stars are not forever beyond our reach. This is a profound truth about our situation in the cosmos. We are not trapped, we are not confined, we are not prisoners of our planet or our solar system. The universe that seems so vast and hostile is actually accessible to us if we have the courage and the capability to explore it. Whether we will actually make these journeys, whether humanity will ever build the spacecraft, develop the technology, find the motivation to travel between the stars, remains to be seen. It might happen in centuries, it might happen in millennia, it might never happen if we destroy ourselves or choose a different path. But it could happen. The physics allows it, the universe permits it, the stars are waiting. How far can humans actually travel in space before they die? Farther than you think. Farther than seems possible. farther than the intuitive limits that constrain our imagination. The edge of the observable universe in a human lifetime, the entire cosmos, accessible to anyone with sufficient technology and sufficient will. A universe of hundreds of billions of galaxies, each with hundreds of billions of stars, each potentially with planets and possibilities, all of it, in principle, within reach. This is the astonishing truth that physics reveals. Not a prison, but a gift. Not barriers, but pathways. Not limits, but horizons that recede as we approach them. The universe is vast, the distances are immense, the challenges are enormous, but we can go farther than we think, and perhaps someday we will.